In the last class, we discussed the importance of like optimum filter, and at the same time, what is the threshold used for optimum filter, and we calculated the probability of error for optimum filter, and at the same time, simultaneously, we calculated the transfer function as well as the output SNR for optimum. Okay, so in the today's class, we can discuss the importance of matched filter and what is meant by matched filter and what is the basic difference between the matched filter and the optimum filter. Okay, and we'll calculate the probability of error for matched filter receiver in this today's session. And at the same time, we can calculate the transfer of filter. After completion of module, each and every student should be able to calculate the probability of error for matched filter receiver. Now, let us go into the concept of matched filter. So, I think we calculated, because we calculated the optimum filter transfer function as well as we calculated the SNR. We got the SNR for optimum filter as a probability of error is equal to half ERFC of x01 of t minus x02 of t divided by 2 root 2 sigma. Okay, where x01 of t minus x02 of t divided by sigma is nothing but the square of output SNR. Okay, is nothing but the output SNR, and we focused on very much, we considered rho factor and we assumed it as x01 of t minus x02 of t divided by sigma whole square. That is square of output SNR, we assumed it as rho. Okay, and also based on the Schwarz inequality. So can any one of the student please tell me what is the Schwarz inequality? I request any one of the student kindly interact and tell me what is Schwarz inequality. Have we studied in the case of optimum filter? Have we used the Schwarz inequality in the case of optimum filter? I will tell you that we used for the calculation of probability of error. Can any one of you tell me what is the Schwarz inequality?
Integration minus infinity to infinity theta 1 of x into theta 2 of x whole square is less than or equal to integration minus infinity to plus infinity modulus of theta 1 of x whole square into dx, integration minus infinity to infinity modulus of theta 2 of x whole square into dx.
Okay, very good. So you can conclude that this Schwarz inequality is valid for in both the time domain as well as frequency domain. Very good. Can you tell me the probability of error expression for optimum filter we calculated in the last class? Can you tell me the expression for probability of error?
Yes, ma'am. 1 by 2 ERFC of x01 of t minus x02 of t by 2 root 2 sigma.
Very good. What is rho? We considered some factor rho. What is that rho?
Yes, ma'am. Rho is
Rho is
x naught
square
t
of
by
output
sigma whole square.
Yes, very good. That is square of output SNR whole square. So that
Yes,
okay, ma, thank you. With that internal factor, we assumed it as rho. Okay, rho square, which is x naught of t sigma whole square, where x naught t is nothing but change in the output signal, and sigma is nothing but the standard deviation, and sigma square will be the variance. Okay, so using optimum filter equation for transfer function of optimum filter. See, we calculated the transfer function of optimum filter using the validity equation of Schwarz. Okay, here Schwarz inequality is valid. I already told you Schwarz inequality is valid whenever theta 1 of f is equal to k times that of complex conjugate of the second function. So first function is equal to k times that of theta 2 star of f. Okay, here you can assume that what is theta 1 of f? In the last class, while calculating the probability of error for optimum filter, theta 1 of f is defined as h of f into SNI of f. and theta 2 of f will be x of minus f divided by root Sni of f into e power minus j omega. Okay, this is theta 2 star of f. Already we calculated the same in the case of optimum filter. Now, what is the transfer function of optimum filter? In the last class itself, we calculated the transfer function of optimum filter using this validity equation of Schwarz inequality. So Schwarz inequality, what is Schwarz inequality? As we discussed, it is the square of integration of product of two functions. It is always less than or equal to product of integration of squares of individual functions. So that is valid for both time domain as well as frequency domain. And our theta 1 of f will be, for example, if you take the first function as theta 1 of f and second function as theta 2 of f, theta 1 of f will be k times that of theta 2 star of f, where theta star represents the complex conjugate. So just we substituted the assumed functions of optimum filter. Theta 1 of f is equal to k times the of f, where theta 1 of f is equal to f into root Sni of f. It is k times that of x of minus f into Sni of f into e power minus j omega t. Okay, so here we assumed the transfer function of optimum filter as h of k into x of minus f, k x of minus f of f into e power minus j omega. So in the case of matched filter, input noise power spectral density, it is always white in. What is the basic difference between the optimum filter and matched filter? In the case of matched filter, the input noise is all power distribution is always uniform. Then we can say that the corresponding noise is called as white noise. Matched filter, the input noise power spectral density is white in nature. So we know that the white noise has power spectral density, which is equal to n, n0 by 2. Therefore, the transfer function of matched filter is equal to k into x of minus f. Take this Sni of f as n0 by 2. So divided by n0 by minus j omega t. So it will be equal to 2k by n0 into x of minus f minus j omega t into e power minus j omega t. Our transfer function. So I kept it in one. It represents that that is the corresponding expression for function of matched filter. Just we took the same expression transfer function and we replaced the input noise power as n0 by 2 because density of white noise is equal to uniformity is assumed as n0 by, that's why we'll n0 into x of minus f into e power minus j. Now what is the transfer function of matched filter? And shown here. Just we replaced Sni of f as n. We took the same expression of optimum filter. Sni of f as 2. Now let us calculate of matched filter. I think every student is familiar with between the impulse response and transfer function between impulse response and transfer function of a filter. Transfer function h of f, it is defined as the ratio of output voltage to that of input in terms of frequency domain. H of f, ratio of output voltage to in frequency domain. So h of f is the response of the particular matched filter domain. In time domain, if you want, you can impulse response. So impulse response small h of t is the inverse Fourier transform of function. So what is the relation between transfer function? H of t is equal to inverse Fourier of f. So in the last slide we calculated the transfer filter. In this slide we are going to calculate the impulse of matched filter, which can be obtained by taking a transform of transfer function. So for that, already I told you the input noise power is white in nature. So the white noise has uniform power which is n0 by 2. So get the impulse response of the transfer function integral minus infinite to plus infinite h of e power plus j omega j 2 pi ft dt. It is impulse response. It is response. So the impulse response of is, what is the impulse response? Integral minus to plus infinite h of f into e omega t. Okay, where omega we replaced as 2 pi, we replaced omega as 2 pi f. Simplify it as integral minus infinite to plus infinite into e power j 2 pi f t df. So it is equal to of as 2k by n naught into x of into e power minus j 2 pi f t. Okay. Integration of h of f into e power j 2 pi f t. Substituted h of f as the same expression into j 2 pi f t dt to integral minus infinite to plus infinite f into e power j 2 pi of into t minus t, capital T minus t. Capital T is the bit duration. Capital T as bit duration. Just here we represent.
Ma'am.
We have minus f.
Ma'am, PPT కనబట్టలేదు మ్యామ్.
కనిపించట్లేదా? Please wait. Sir, net on చేయండి. Please wait for 1 minute. Actually, net వస్తుంది. Achit, now is it okay or it's not visible?
No ma'am, not visible ma'am. చాలా సేపటి నుంచి ఇలాగే ఉంది మ్యామ్.
Actually మనం
మ్యామ్ నాకు వస్తుంది మ్యామ్.
నువ్వు నెట్ చేంజ్ చేయవా? క్లాస్ అయినంత సేపు కాసేపు సిమ్2 సిమ్2 Now is it visible? Please
No,
respond,
ma'am.
one of you. No.
No.
Not visible. Please wait for a few minutes. పెట్టు. But now is it visible?
Yes, ma'am.
Okay. Okay, thank you. So మీకు ట్రాన్స్ఫర్ ఫంక్షన్ స్లైడ్ యాక్చువల్గా మీకు ఇప్పుడు అర్థమైందా ట్రాన్స్ఫర్ ఫంక్షన్ కెన్ బి మూవ్
మ్యాచ్
టు
టు
ఇంపల్స్
ఫిల్టర్
రెస్పాన్స్
ట్రాన్స్ఫర్ ఫంక్షన్ దాకా ఓకే మ్యామ్.
ఏమ్మా ఎక్కడి వరకు
మ్యాచ్ టు ఫిల్టర్
Match
ట్రాన్స్ఫర్
filter.
ఫంక్షన్ వరకు కనిపించింది.
Okay, okay. So what is the transfer function? Just I will once again recollect. So what is the transfer function of matched filter? So it is calculated based on the equation of transfer function of optimum filter, because that it is matched filter is same as the optimum filter, but what is the difference? Here the the input noise power spectral density is white noise. So that's why we took the same expression for SNI of f as N0 by 2. Same expression we took and we replaced SNI of f as N0 by 2. Therefore, the transfer function of matched filter will be 2k by N0 into by N0 by 2. Input noise for the matched filter is, its distribution is uniform. So we called it as white in nature. Therefore, we obtain the transfer function of matched filter as 2k by N0 into x of minus f into e power minus j omega t. Now, we used this expression to calculate the impulse response of matched filter. So, how can we calculate the impulse response? So, we can obtain the impulse response of transfer of any filter by taking the inverse Fourier transform to the transfer function. Okay, because impulse response is h of t. It is defined as inverse Fourier transform of the corresponding transfer function, where transfer function is h of f. I think you know what is transfer function. It is defined as a ratio of output voltage magnitude to input voltage magnitude in terms of frequency domain. So for matched filter, the input noise power spectral density is white in nature. So we replaced SNI of f as N0 by 2, and we took the same expression for calculating the impulse response. So generally, what is the inverse Fourier transform expression? It is integral minus infinity plus capital X e power k plus dt. Okay, so what is h? H of f is the transfer function. Just replace the corresponding expression. We got it as 2k by N0 x of minus f into e power minus j 2 pi ft into e power plus j 2 pi ft df. Okay, so it is equal to 2k by N0 integral minus infinite to plus infinite x of minus f into here in this equation we have negative frequencies. Okay, so the corresponding representation is of it's not on the positive real frequency axis, it is on the negative real frequency axis. So that's why we represented as here we took in the e power exponential term, we took minus f as common. So this is e power minus x into e power plus y. So you can call it as e power minus of x minus 5. Okay, so we represented it as minus f, e power minus f into capital T minus small t, capital T minus small t into df. Okay, what we did here, we represented the negative axis, negative real axis. So minus and so that you will have, if you take minus f as common, you will get capital T minus small t, where capital T is the bit duration, where capital T is the bit duration. So it will be equal to 2k by N0 x of, so this if you observe this whole equation, it is integral minus infinite to plus infinite capital X of minus f into e power j 2 pi of minus f into capital T minus small t df. If you observe this equation, it is nothing but the Fourier transform of, capital T minus small t, inverse Fourier capital T minus small t. So that's why we replaced this whole function as small x of capital T minus small t. This is nothing but the input signal, shifted input signal by bit duration, So it will be because the input signal is nothing but the difference between the two levels, that is positive magnitude and negative magnitude. Okay, so x1 of capital T minus small t plus minus, that is difference. So x2 capital T minus small t, because total magnitude is the total magnitude will be like a positive magnitude minus negative magnitude. So negative magnitude will be minus a, and positive magnitude if it is plus a minus of minus a. So it will be 2a. So total magnitude will be from minus a to plus a. So that's why we can represent x of small x of capital T minus small t as a change in the input signal. So that's why we represented as difference between the positive level magnitude and negative level magnitude. So what is h of t? H of t is an impulse response, which is the inverse Fourier transform of transfer function. We used the same expression for transfer function, and we obtained it as 2k by n naught into shifted input signal. We can replace input signal as the difference between the two signal levels, that is positive magnitude level as well as negative magnitude level. Is this okay to everyone? Can we move to the next slide? See, please, one of you respond. Is it okay? Can we move to the calculation of probability of error for matched filter? Okay, ma, thank you. Okay, just for the knowledge sake, we calculated the transfer function as well as impulse response of matched filter by replacing the input noise power spectral density as a white noise, which is equal to n naught by 2. Now, see, I wanted to tell you one thing. From this section onwards, from this module onwards, the probability of error calculation for each and every system, that may be binary ASK, binary FSK, or binary PSK or QPSK, whatever may be the system, will follow the same procedure. Please listen this carefully so that you can do automatically the probability of error for ASK. Everything you can do. Just listen how listen the step by step analysis so that you can easily understand the probability of error calculation for the remaining systems. Every time we'll take the probability of error for optimum filter, because our intention is to attain the optimum SNR, that is the highest SNR, so that we can reduce the probability of error. Okay, so because we assume, have we calculated the two thresholds? One is upper threshold and lower threshold based on the assumed threshold value as average of two output signal levels, and we got the probability of error as half ERFC of x01 of t minus x02 of t divided by 2 root 2 sigma. Here capital T, what capital T represents? Capital T represents the bit duration. Here we are observing the analysis at one particular instant, at time instant, small t is equal to capital T. This is the general expression for probability of error for optimum filter, which we calculated in the earlier last class. Okay. So for optimum filter, already I told you the square of the output SNR should be maximized. So that's why we considered x02 of t as some x0 of t. Which is the change in the output signal magnitude. Similarly, x of t will be change in the magnitude. Okay, and here x0 t signal magnitude, which is x01 of t minus x0 divided by 2 divided by sigma only. We are focusing on output SNR. We are focusing on square of. So that's why x0 of t divided by sigma whole square. The same point in the optimum filter, rho max is assumed of t by sigma whole square divided by sigma whole square, where divided by sigma is nothing but the output SNR, and where SNR is assumed as rho max. Why the max suffix? The suffix y we represented max. Our intention is to maximize the square of output. If to maximize this internal function of complement, if you maximize of complementary error function, you can reduce the error, because there exists a like inverse relationship between probability of error and output SNR. Naught of t divided by sigma whole square as rho max. So this is an square. This is not the output SNR. This is SNR. So while substituting the corresponding value in expression, you should apply root for this rho. The root rho max will be substituted here to get the probability for the particular system. For the optimum filter, what is the assumed value? Square of SNR is assumed as rho max. You should maximize that rho max. The value is x naught of t divided by 6. Already we calculated the same value for and for optimum filter we obtained the square of output as integral minus infinite to plus infinite of f divided by SNI of f whole square of f square divided by SNI of f into df. If you go through the corresponding module in the last class, we calculated this expression, that is the square of output SNR, and we got it as integral minus infinite to plus infinite x of f square magnitude divided by SNI of f into df. Okay, for matched filter, the input noise power spectral density is white in nature. The see, for matched filter, just we substitute the value of SNI of f as n0 by 2 in the general expressions of optimum filter. So that's why here SNI of f will be n0 by 2. So therefore, the maximum value of square of output SNR of matched filter will be rho max is equal to integral minus infinite to plus infinite x of f square divided by n0 by 2, which is equal to, in denominator you have n0 by 2. So if you take it to the numerator, you will get 2 by n0. You will get 2 by n0. So it is equal to 2 by n0. 2 by n0 integral minus infinite to plus infinite mod x of f square into df. What is x of f? X of f is the frequency or the Fourier transform of the input signal x of t. What is x of f? Fourier transform of input signal x of t. So the magnitude square will be into df will be our rho max. So 2 by n0 integral minus infinite to plus infinite mod x of f square df. Please remember this expression. So you can directly substitute the values of x1 of t and x2 of t in this expression to calculate rho max, and once you obtain rho max, the same will be substituted in the probability of error to calculate the corresponding expressions for PE. Okay, so please remember this expression. So you got rho max, which is the square of output SNR, as 2 by n0 integral minus infinite to plus infinite mod x of f square into df. So here Parseval's theorem states that, so please remember one theorem. It states that magnitude square of integration of a particular function in frequency domain is equal to the same function in time domain. So what is Parseval's theorem? It states that the square of magnitude of a particular function in time domain and frequency domain both are same. The magnitude of square of magnitude of a particular function in frequency domain and time domain are equal. So that's why we replaced integral minus infinite to plus infinite mod x of f square into df. You can replace this as integral minus infinite to plus infinite magnitude of x of t square dt. So that's why you can replace this x of f square magnitude as mod x of t square, So using Parseval's theorem in the maximum value, so use this Parseval's theorem in the maximum value for square of output SNR. So use this Parseval's theorem in the maximum value of in the square of output SNR. In the square of output SNR for matched filter. Okay, for matched filter, you directly using Parseval's theorem in the square of output SNR equation for matched filter, we can obtain rho max as 2 by n naught integral minus infinite to plus infinite mod x of f square df. So you can replace this mod x of f square df as mod x of t square dt. So what is Parseval's theorem? Parseval's theorem states that the square of magnitude of signal in frequency domain and time domain, the magnitudes are same. So that's why we replaced mod x of f square df as mod x of t square dt. Now this is our final equation. So rho max will be 2 by n naught integral minus infinite to plus infinite x of t square dt. Now based on the value of x of t. So what is x of t? X of t is the change in the magnitudes of input signal, because small x represents the input signal, and x of t you can replace as a difference between the magnitudes of higher level and lower level. So that is x1 of t. This is the higher magnitude minus lower magnitude is x2 of t. So you should remember one point, that the magnitudes of x1 of t and x2 of t are same. Okay. So but differed in direction, like phase. Okay. So x1 of t minus x2 of t. If you take like that, you will get total sum, because x2 of t will be equal to minus x1 of t in general. So this is in the form of a minus b whole square. A minus b whole square, the magnitude of a minus b whole square. So just I split the corresponding expression as a x square plus y square plus 2xy. So x is x1 of t. So x1 square of t plus x2 square of t minus, here it is minus. This will be minus, this is not plus actually. Okay, anyhow I will replace here, this is not plus, this is a minus b whole square. So x1 square plus x2 square minus 2 x1 of t into x2 of t dt. Okay. So take this as negative sign. Okay. So I will replace it later. Once again I did like that. So we obtain the maximum value for the square of output SNR as 2 by n naught. Here you can do one thing. Okay, please wait for 1 minute. That is in the form of x1 of t minus x2 of t square. Okay. So take that as okay, here I did this. This is x1 of t minus, not plus. Okay. Similarly, here this will be rho max. Okay, this is x1 of t minus x2 of t square. Okay. So you will obtain it as like this. And here also I have to do the same thing. So I am changing the contrast and brightness so that it's not visible to the students. That's why I am doing like this. Okay. Now let us go to the slide. Okay, this is in the form of x1 of t minus x2 of t square. This is a minus b whole square form. So x1 square of t plus x2 square of t minus 2x1 of t into x2 of t dt. Okay. So this is our square of output SNR. Please always remember, this rho max is the square of output SNR. So we obtain the maximum value for square of output SNR as rho max is equal to 2 by n naught integral minus infinite to plus infinite, same value I mentioned, that is x1 square of t plus x2 square of t minus 2x1 x2 dt. Okay, so let us assume here already you know that the magnitude of x1 of t and x2 of t magnitudes are always same, because while calculating the in the case of baseband signal receiver, and we assumed x1 of t is plus a and x2 of t as minus a. Even while analysis of optimum filter we did like that. X1 of t magnitude is equal to x2 of t, but it differs in the direction. So x2 of t will be minus a and x1 of t is plus a. But let us, this is square. So once it is squared, once the magnitude is squared, the energy will be same. Okay. So let us assume the energy of the first signal x1 of t as E1. What is x1 of t? x1 of t is the positive magnitude, and let the energy of negative magnitude, that is x2 of t, be E2. And the energy formed due to the two signals x1 of t and x2 of t. Actually here I have stated two signals because those two are differed in magnitudes. Okay. Otherwise we if you then that is generally called as autocorrelation function. So using the autocorrelation function, you can obtain the energy as integral 0 to t x1 of t into x2 of t dt. If those two have no similarity in the magnitude, one is x1 of t and other is x2 of t. So let us assume E1 is equal to E2 is equal to minus E1 2, because x1 of t square, if you do, this is positive magnitude, so there is no problem. And coming to x2 square of t, x2 is generally minus a. If you square that one, the value is same as that of E1. So that's why E1 value is equal to E2 in general. In general, the energy of the signal x1 of t, where signal x1 of t is of magnitude plus a, it is equal to signal magnitude, that is the energy of x2 as 2 by n naught integral minus infinite to plus infinite x2 square of t. Okay, and similarly E1 2 is equal to integral 0 to t x1 of t into x2 of t. Here x1 of t is positive magnitude and x2 is of negative magnitude. So obviously the energy obtained from this autocorrelation function is negative. So that's why we assumed like E1 is equal to E2 is equal to minus E1 2. Minus E1 2 is equal to EB. Okay, what is EB? EB is the bit energy. EB is the bit energy, because we are calculating for a particular bit interval. If you calculate for a particular bit interval, it will be, we assume it as EB, where EB is the bit energy, which is the product of PS and TB, where PS is the power dissipated per symbol and TB is the bit duration. So E1 will be equal to E2 is equal to minus E1 2 is equal to EB. If you assume like this, that assumption is based on the corresponding values of E1, E2, and then the square of output SNR will be, so what will be our square of output SNR? Please substitute all these values in the expression of maximum value for square of output SNR. That is rho max. So rho max will be 2 by n naught. This is integral minus infinite to plus infinite x1 square of t dt. That will be EB, plus similarly integral 0 minus infinite to plus infinite x2 square of t dt. This, if it is for bit duration, it will also be equal to bit energy. Next, minus 2 AB. AB is the product of positive magnitude and negative magnitude. You can analyze the energy by using the autocorrelation function, and we assume it as E1 2, which is equal to minus EB, because minus E1 2 is EB. So E1 2 will be minus EB. So minus 2 into minus EB. Okay, so it will be 2 by n naught. Here it will be plus 2 EB. So plus 2 EB plus 2 EB. So it will be 4 EB. So it is equal to how much? 8 EB by n naught. 8 EB by n naught. So if you assume the energy E1 magnitude as positive and E2 magnitude as negative, okay, and E1 2 will be minus EB. Okay. but the magnitudes of E1, E2 both are same, but differs in the direction, changes in the phase. So finally you got the square of output SNR as 8 EB by N naught. Now all of you please substitute. See, we got a rho max as 8 EB by N naught. We obtained a rho max as 8 EB by N naught. But actually in the expression for probability of error, if you observe, it is half ERFC of x naught 1 of t minus x naught 2 of t divided by 2 root 2 sigma. What is output SNR here? Change in the output signal, that is x naught 1 of t minus x naught 2 of t divided by change in the output noise component, that we assume sigma. So therefore you can obtain the output SNR by taking the root of square of output SNR, that is root rho max will be our output SNR. So rho max is the square of output SNR. From starting onwards we assumed it as x naught of t by sigma whole square, and we obtain that as integral minus infinite to plus infinite x of f divided by SNI of f df. We use the same expression, but that is square of output SNR, but actually here we need the output SNR. So that's why we took root of rho max. So output SNR is defined as change in output signal divided by change in the noise component. Okay, so it will be equal to rho max, root rho max, but rho max we obtained it as 8 EB by N naught. So it will be root 8 EB by N naught will be our output. Now we define the same probability of error expression for optimum filter. It is defined as half ERFC of x naught 1 of t minus x naught 2 of t divided by 2 root 2 sigma. But x naught 1 of t minus x naught 2 of t divided by sigma is how much? Root EB by N naught. This is for the matched filter. Now the probability, please substitute the x naught 1 of t minus x naught 2 of t divided by sigma by using root rho max expression. You can obtain this, please substitute in the probability of error expression, and so it will be half ERFC of root of, okay, please wait, root of, this is not like this, this is a root, because this is x naught 1 of t minus x naught 2 of t divided by sigma is root 8 EB by N naught, root 8 EB by N naught. Okay, please wait for 1 second. So this is the root like this, not the one stated there. So you can use the same expression. So the probability of error is obtained as half ERFC of x naught 1 of t minus x naught 2 of t divided by 2 root 2 sigma. But we obtained the output SNR as root of rho max, Okay, so where root rho max will be root of 8 PS into TB, 8 PS into TB. So it will be half ERFC of root 8 PS into TB divided by N naught, where PS into TB is nothing but bit energy. So root 8 is nothing but 2 root 2. Root 8 is 2 root 2. So here 2 root 2 gets cancelled. So you will get probability of error as root EB by N naught, root EB by N naught, where root EB, you can also write like this, where bit energy is obtained as, where bit energy we consider it as PS into TB, or else you write like this. Okay, so if you see this, probability of error is obtained as half ERFC of root of 8 PS into TB divided by N naught. This is nothing but root rho max, that is root of square of output SNR divided by 2 root 2, divided by 2 root 2. So probability of error for matched filter is obtained as half ERFC of root this PS into TB is EB. So root 8 is 2 root 2. So 2 root 2 gets cancelled. So you will get it as half ERFC of root EB by N naught. So where EB is the bit energy which is obtained as PS into TB. Now with this we can conclude, with this we can like complete the probability of error for matched filter. So is this okay to everyone? We'll follow the same procedure. How we did? We considered the probability of optimum filter and then we calculated the x01 of t minus x02 of t divided by sigma whole square. That is nothing but rho max. We calculated that using Parsel's theorem. We used the same expression for optimum filter. And then after calculation, we applied root of rho max and we substituted that x01 of t minus x02 of t divided by sigma as root rho max, and root rho max divided by here leftover term is 2 root 2. So the 2 root 2 and numerator we have root 8. So both gets cancelled and you will get root EB by N naught. Now, so this is all about the probability of error as well as the transfer function for matched filter. So the only thing here is we replaced assumed the input Gaussian noise distribution as uniform. That is uniform. So we assumed it the magnitude as N naught by 2. Okay. So with this module, you should be able to derive the expression for output SNR, transfer function, and probability of error for matched filter receiver. Okay. Now, can any one of the student please tell me what is the probability of obtained value? What is the probability of error expression for matched filter? How much we got?
1 by 2 ERFC root over EB by N naught.
Can you tell me the probability of error expression for general baseband signal receiver? That is a module 1. General baseband signal receiver, how much you got? What is the probability of error for baseband signal receiver?
Is
We
also same,
almost we
1 by
obtained the
2
same expression. 1 by 2
ERFC root over EB by N naught. Same.
సేమ్ వచ్చిందా చూడండి ఒకసారి సేమ్ వచ్చిందా మాడ్యూల్ 1 okay in the next classes and what is Parsel's theorem మా చెప్పండి ఒకసారి what is Parsel's theorem we obtain the output SNR as 2 EB by N naught for baseband signal receiver, and we calculated the probability of error, and we obtained it as okay root EB by N naught. And what is the probability of error expression for optimum filter to get optimum response? What is the probability of error? Achyut.
Ma'am.
What is the probability? Cheppandi. What is the probability of error expression for optimum filter?
Half ERFC of into x x1 x output of 1 of t minus x02 of t by 2 root 2 sigma.
2 root 2 sigma. Okay, very good. Okay, we used Parsel's theorem and we assumed like this, and we calculated the probability of error for matched filter, and we obtained it as half ERFC of root EB by N naught. Now, in the next classes, we'll calculate the probability of error for ASK. How we'll do? We'll follow the same procedure, but here x1 of t will be AC cos omega ct and x2 of t will be 0. Just we'll substitute the corresponding values of x1 of t and x2 of t. Okay, and for example, in the case of PSK, what we'll do? We'll substitute x1 of t as AC cos omega ct, where AC is root 2 PS. Or else you can substitute in terms of bit energy if you want. Directly you can replace it as root 2ps cos omega ct and x2 of t as minus root 2ps cos omega ct. So like that we will substitute all the corresponding values. In FSK we will substitute like root 2ps cos 2 pi fht and this as AC like root 2ps cos 2 pi flt. Okay, like that we will solve. Okay, anyhow we can discuss the probability of error calculation for ASK in the next class. So any doubts?